You've probably never heard of NATS, but you've probably used one of our services at some point, because NATS is the company responsible for air traffic control services in the UK. So there are, broadly speaking, 3 different kinds of air traffic control service that NATS provides. The first of those is services in and around airports. The second is en route services, so anything that flies between 2 airports in the UK or flies into UK airspace or out of UK airspace will be controlled by a NATS controller. The third class of air traffic control is oceanic control, and what that means is that anything which flies over the eastern part of the North Atlantic is also controlled by a NATS controller. So I'm not an air traffic controller, but I'm a statistician for their operational analysis department. And it is the third class of air traffic control, the oceanic control, which I'm speaking about today. So, to give you a bit of background on air traffic control, if an aircraft is above UK airspace, it's under radar control. And what that means is that the controller has a radar screen in front of them and is consistently updated with the position of the aircraft. When an aircraft is flying over the North Atlantic, they're not under radar control, and so they operate instead under a type of procedural control. And what that means is that the controller puts them on a track across the Atlantic airspace, and they will stay on that track until told to do something different. To maintain the safety of the airspace, the aircraft are separated in each of the 3 dimensions. So they have to maintain vertical, lateral and longitudinal separation minimum. And you can think of these separation minima as a sort of exclusion zone around each of the aircraft. In the vertical direction, the aircraft should be separated by at least 1,000 feet, so that is how far away from each other the North Atlantic tracks are placed. In the lateral direction, the aircraft are separated by 60 nautical miles, so that's how far away from each other laterally the North Atlantic tracks are. And at the moment, the longitudinal separation for any 2 aircraft flying on the same track is 10 minutes separation. So the leading aircraft should be at least 10 minutes in front of the following aircraft. And as it is a type of procedural control, the aircraft report their positions back to the controller whilst en route. And the way that we assess the safety of this airspace is to compare the estimated collision risk to a target level of safety. So under the current concept of longitudinal separation minimum, this is what happens when aircraft report. There are waypoints which are positioned every 10 degrees of longitude across the North Atlantic. And an aircraft reports back to the controller every time it reaches one of these waypoints. And what that means is that the controller receives a positional update on where the aircraft is roughly every 43 minutes. For aircraft flying in trail, so where one aircraft is following another, what would happen would be that the leading aircraft, the orange aircraft, has reported at waypoint 0. The following aircraft, which is the green aircraft, reaches waypoint 0 10 minutes behind the leader. And it would report at that waypoint, wait until it got to the next waypoint and report again. So they're reporting asynchronously in time. The question that we were trying to tackle through this particular piece of analysis was what would happen to the risk of the airspace if the separation of the aircraft was decreased. Specifically, what would happen if the aircraft didn't report at the 10-degree longitude waypoints, but reported periodically in time? And what would happen if the longitudinal separation minimum was halved, so if it was decreased from 10 minutes down to 5 minutes? And we were looking at whether or not, using these changes or under these changes, the airspace would remain safe. So under the proposed concept, you would have more frequent reports over the same space. And for 2 aircraft flying in trail, you would have both more frequent reports, but also a halved longitudinal separation minimum. So, the way that we assess risk in the North Atlantic is by using the Reach Collision Risk Model, which derives from a paper published in the Journal of the Institute of Navigation in 1966. And the Reach Collision Risk Model can be broken down into its 3 different dimensions. So there is a vertical version, a lateral version, and a longitudinal version, and it's the longitudinal form that we considered here. And what the Reach model gives us is an estimate of the number of fatal accidents per flight hour in the North Atlantic airspace for given separation standards. And all it is a sort of product of different terms relating to probabilities and relating to the dimensions of aircraft. So the first 2 terms in the model relate to the probability of lateral overlap and the probability of vertical overlap whilst in the airspace. And what they mean is that if you have 2 aircraft that are nominally assigned to the same track, they should in theory be flying directly behind one another. But due to track keeping ability and due to height keeping ability, there can be some variation around that. And what the Reach model does is encloses each of the aircraft in a box of the standard size. So you've got the standard length, breadth and height of an aircraft. And you have vertical and lateral deviations from the oceanic track. And because of the height keeping, the rear aircraft can vary from its proposed height, and it can also vary laterally from its proposed track. But it's not just the following aircraft that has these variations, it's also leading aircraft. So both of the aircraft are sort of bobbing around what their proposed positions are, and it means that they're not always in overlap. The next terms in the model relate to the average dimensions of the aircraft, so that's the sort of box that's placed around them, and to the closing speeds. And the closing speed is the difference between the longitudinal vertical and lateral speeds at the point of impact. There's a term in there for the reporting period, which is what we're varying for this particular study. And finally, there's a term in there for the probability of longitudinal overlap, and this is the one that we really had to estimate using statistical methods. So all of the terms in this circle here are sort of known at the moment, and the final term in the model has to be estimated. And what the probability of longitudinal overlap comes down to is a function of the initial separation between aircraft when they're placed onto the tracks and the likelihood of losing that separation during one reporting period. So for the initial separation, it's important to realise that aircraft will not always be placed on the oceanic track structure at exactly their minimum separation. So if there is a 5-minute separation, they'll be placed on at 5 or 6 or 7. It'll always be 5 or more. So to model this distribution of the way that the aircraft would be placed onto the track, what we did was used a gamma distribution and called it the buffer distribution, with the benefit being that it has both a shape and a scale parameter that we could vary to sort of vary the shape of the buffer distribution. And since reduced longitudinal separation minimum isn't a reality at this stage, we need something that's quite easy to vary. So what we said here was that as a baseline assumption, we would assume that aircraft were on average separated at 2 minutes above the separation minimum. So for a minimum separation of 5 minutes, that means that typically they're put on at 7. The second term in the probability of the longitudinal overlap is the likelihood of losing separation during one reporting period. And what we do is derive this from what we call an overall error distribution. The overall error distribution comprises 2 components, the initial error and the reporting period error. The initial error is the difference between the estimated and the actual separation at the time of the first reporting point. So if you consider this distance time plot, the first 2 black dots relate to the first report, the second 2 black dots relate to the second report. So what you have is the leading and the following aircraft both reporting at time n-1. And from that, we can predict the path of the leading aircraft and track back to where that was at the same distance from the waypoint as the following aircraft. And what that gives you is a prediction of the time-based separation at the time of the first report. Both of the aircraft then report 20 minutes later, or whatever the reporting period is. And then from that we can form a view of how fast the leading aircraft has actually been going, so we can track the actual path of that aircraft. And we can also track the actual path of the following aircraft. And what those then give us is the actual time-based separation at the time of the first report. And the difference between that actual separation and the estimated or the predicted time-based separation is the first component of the overall error, that is the initial error. Using the actual paths, we then also find the time-based separation at the time of the second report. So if that is equivalent to Sn, and if the previous separation is equivalent to Sn minus 1, then if Sn is less than Sn minus 1, then a loss of separation has occurred. And that loss of separation is the reporting period error, so that is the second component of the overall error distribution. So what we had to do was estimate what the shape of this distribution would be. And for this we used a double exponential. Now the reason that we used the double exponential was because we derived it from known information on aircraft which currently cross the North Atlantic. So the fit of the distribution was tested, it was just then the parameters for that distribution that had to be estimated. And you can see there that the scale of this distribution will be affected by certain parameters, and in this case the shape is affected by the reporting period, the length of time taken to resolve a conflict should it occur, the initial separation of aircraft. And so what that means is that the larger the value of the shape parameter, or therefore the larger the variance, the more probability you'll have in the tails. So if you consider the x-axis to be the separation between aircraft when going onto the tracks, the probability in the tail is the probability that they'll lose their separation. So you recall that the probability of longitudinal overlap is a convolution of the two distributions that I've just shown you, the initial separation and the likelihood of losing that separation. So it's a convolution of the gamma and the double exponential distributions. And so given that we've now got these, by double integration we can get this expression for the probability of overlap and put that into the collision risk model. And so the probability of longitudinal overlap turns out to be a function of the minimum separation allowed, the scale of the double exponential distribution, and the shape and the scale parameters of the gamma. What we then had to do was make some baseline assumptions as to what these parameters that affect the distribution would be. So we assumed that the average time taken by a controller to resolve a conflict would be 9 minutes, and that the aircraft performance standard that the aircraft over the North Atlantic would comply to is required navigational performance 0.5. And what that means is that aircraft are within half a nautical mile of their tracks for 95% of their flight time. And so from this, we then derive what the number of fatal accidents per flight hour are using the reach collision risk model. So we've now got the term in blue. And what we end up with is some risk curves that look like this. So what you have here is 5 different initial minimum separations between aircraft. So it ranges from 4 up to 8. On the x-axis, you've got the reporting period. So that is what the risk associated with a particular minimum is for a particular reporting period. And then the y-axis is the number of fatal accidents per flight hour, and it has been put on a logarithmic scale. As I said at the beginning, we measure risk against a target level of safety. So if you then put a target level of safety across this graph, then the break-even point, so the point where each of these curves hits the target level of safety, is the largest number of minutes for which a reduced longitudinal separation minimum is considered safe. And you can see that that number of minutes increases as you increase the minimum separation between aircraft, which is what you would expect. So to come back to the original question, which was whether or not a 5-minute reduced longitudinal separation minimum with 20-minute periodic reporting would be supported. The answer is yes, because periodic reports must be made every 23 minutes or less for this particular longitudinal separation minimum to be considered safe. And obviously it didn't end there. We carried out some sensitivity analysis relating to the performance standards, relating to the response time, and relating to changes in the shape of the initial distribution when aircraft are placed onto the tracks. And what we found was that 20-minute periodic reports under a 5-minute longitudinal separation would be consistently considered safe. And now I'm happy to take any questions you might have.
To give it more context for you, what we're actually dealing with is trying to improve the diagnosis of child abuse. So specifically, we're looking at bruises and saying, when children present with a bruise at A&E or at a GP's clinic, is that bruise accidental or non-accidental? And the first step of any kind of judgment of that sort is, do we have some standardised, reliable and accurate way of actually assessing that bruise to use that then in the legal proceeding? So, let me see if very good. Right, so this is a project team. We call ourselves Protect. And you can see a diverse range of people right from the front end. We've got the research nurses who deal with the children and collect the data. Right through to the back end where us statisticians live, which is what I'll be presenting to you today. So the aims and objectives. The most important fact of all of this work is that bruising is the most common injury seen in physically abused children. Therefore, it requires clinical and legal recording, and that needs to be accurate and reliable. Currently, there's no standardised procedure in place for assessing bruises in children. So our first protocol is to investigate what kind of variability we're seeing in and between, or within and between observers, which is exactly the aim of this study. I'll be using both printed and digital images, so that means hard copy photographs and also on-screen laptops, to see if there's a difference in modality between assessment and variability. And also an important point is that there's no right answer for any of this work. We don't know what the colour of the bruise is, what size the bruise is. That's the whole point. What we're dealing with here is observer variation and consistency, and not so much error rates. So the methodology. We set up a day. We asked people to come along to assess these printed and digital images of bruises. It took about 10 or 20 minutes per person, and we had 64 people turn up in total, which was fantastic. Of those 64, we then asked if anyone could come back again. That would be even better, and 45 returned to do the same process with 4 same photos over the 2 sessions, 2 different ones, just to mix it up so that they didn't necessarily spot that they were the same bruise and put the same answers. So we've got 45 we can look at within observer differences, and 64 in the first session for between. Of those images, I'm just going to run through and demonstrate how we maybe did some of the analysis on the data we collected from the day, and this is one of the images. I will point out that this isn't a child's bruise. This is students, medical students, so most likely some drunken injury one night. This is a study in action. So we've got our keen observers at the top there, all working away hard for us. The picture of the bruise on the screen for analysis, and then also this in the bottom right-hand corner is the colour palette. We asked observers to choose what they thought was the most predominant colour in the bruise by picking one of the squares from the colour palette we provided them with. In larger detail, there it is. We had a bit of feedback on it. You can see there's a lot of colours there. The reason we use this colour palette is threefold. The first is it gives a finite range of colours to choose from. Okay, it's 216. It's not a small finite, but it is finite. Secondly, it reduces ambiguity. when people see a colour, they can call it different names. You might get 3 different people calling the same colour pink, rose and magenta. Equally, you can have people talking about different colours and calling it the same name. So it gets rid of that. And the third reason is, I don't know if you can really make out, but in each of these little squares, the top line is a 6-digit hexadecimal code. That relates to the RGB, which is the red, green and blue elements of the colour. The first 2 digits relate to the red, middle 2 to the green, last 2 to the blue. And those 2 digits then transform into a scale from 0 to 255, which defines the intensity of that element in the colour. In order to, one of the advantages of being able to quantify the colour in that way is we can then look at differences between colours, actually get a measure for how different are these 2 colours from each other. So you'll recognise a bit of Pythagoras there in 3-dimensional plane. That's the Euclidean distance. And also I just put a picture up there of the RGB. So the reason it's red, green and blue is they're the 3 primary additive colours. And you can see when they overlap each other, you start getting the other colours. So when red and green overlap, you get yellow. So to try and interpret what the Euclidean distance actually says, I've got some examples up here. So say we start with a colour, which is all the 3s. That's that dark grey in the left there, on the hexadecimal. Those 3s relate to 51 in each of the elements. So our first row there, 51 on the red, green and blue. We've just got 1 colour, so we haven't got any Euclidean distance. And just for the purpose of this slide, we've got a notation. We've got 0 elements, so that's the red, green or blue, moving 0 steps. If we change the blue element of that colour, if we increase it by 1 step, which in this scenario with the colour palette we used is the step of 51, that goes from 51 to 102. Euclidean distance, square root of 51 squared, is 51. Equally, if we then increase the blue element by 2 steps, so from 51 to 153, we get a Euclidean distance of 102. So we're getting some idea as to how much colour difference. I've also put the colours on there so you can see how much colour difference relates to what numbers. The third point to make on this is if we increase all 3 elements by 1 step, so up to 102 for each of the 3, or we decrease all 3 elements by 1 step, so down to 0 in each of the 3, we get the same Euclidean distance of 88.33. But you can see on the graph that they're in opposite directions. You can see from the table they're in opposite directions. So Euclidean distance doesn't allow for direction. It just is a measure of change. So using that theory, we can now look at the variation of colour within and between observers. So I'll start with within. These are the 4 bruises that were the same images in the first and the second sessions. You can see the one I've been talking about is the one on the left so far. Not really sure where these bruises came from. I really think the one on the right is a paintball injury. It looks like that to me. And I've put down the mean Euclidean distance within observers, so between sessions. And to try and interpret what those numbers actually mean, there's 2 main points here. The first is that all of those numbers are greater than 51, so that's greater than the minimum 1 step change in 1 element. The other thing is that they're all less than 88.3, which is a 1 step change in all 3 elements, and also less than a 2 step change in 1 element of 102. So it gives us some idea as to how much colour change we are seeing people choose within or between sessions. Just looking at image 1 then, if we put the distribution up, you can see that a fifth of people, it's quite hard to see on that, a fifth of people, so 1 in 5, say exactly the same colour. They have a Euclidean distance of 0. So morning and afternoon, or in the 2 sessions, they gave exactly the same colour. Another third of people then only gave a 1 step change of 51. So that's the majority, just over 50%, gave a very small change in colour when they saw the bruise at 2 different time periods. Also worth noting, however, is that 9% of the people had a Euclidean distance of 161 over time, which is comparatively quite a large difference. When looking at between observers, just with this one image, of the 216 colours that people could choose from, with 64 people choosing them, we had 12 colours that were chosen from that palette for this bruise as the predominant colour. And when I say predominant colour, it was their perception of the colour and what was predominant about it. Whether it was the intensity of the colour or the most common colour in the bruise was up to them. We just said, whatever you think predominant is. And I've tried to show the colours, see whether you agree with them. 24 people said this colour was the most predominant in the bruise. Another 12 said a different colour. Notice there's actually 3 steps change in those 2 colours. And I've put them on the 3D axes there, just so you can see how they are all clustering in that top right-hand corner. So the other thing we had to look at, other than colour, was measurements. So on the printed images that people had, they were asked to measure what they perceived to be the greatest length of the bruise with a paper tape measure. And they recorded that down in millimetres. They also looked at greatest perpendicular width, but I won't go into that so much now. We'll use greatest length. That table on the bottom shouldn't be there, it's come up too early. Okay, so this is what we're looking at, the greatest length. The average in the first session was 20.56 millimetres, the average in the second session was 20.33 millimetres. And not surprisingly, when we test for the difference between means between the 2 sessions overall for the observers, there wasn't a significant difference. And there wasn't for 3 of the 4 images that were in both sessions. If we did a proxy for what we thought was the between observer standard deviation, so by that I mean if we take the mean of the 2 measurements that an individual gave and look at the standard deviation across those means, we get the middle column on the table. And the within observer standard deviation is then either the square root of the mean square error in the table above, or the 3.7, so the standard deviation of a difference is divided by the square root of 2. And what you can see here is there's actually not too much difference in the standard deviation between either between observer or within observer. It kind of swaps over halfway through. When looking at Image J, now Image J is a software, it's free to download, and it's very, very good at for kind of image analysis and looking at bruises. We asked people to click and draw with their mouse a perimeter around the bruise, like the squiggly red line you can see there. And then Image J can calculate what the ferrule's diameter is, which is equivalently the greatest length. So we can use that for comparison with the manual measurements. The first thing to note is we have a mean measurement in the first session, 21.91, and in the second, 21.86 millimetres. That's slightly higher than the manual measurements. Also, similarly to the manual, we found that there wasn't a significant difference between the means and between the sessions, and that the standard deviation between observers, in this case, is greater than within observers. So comparing the 2 modalities, so comparing manual versus electronic, which is the Image J, just for this one image one now, we can plot them on the same graph and say what did each observer put for each modality, and you can see they're not particularly closely correlated. We've got an R-square of 19.5%, not very strong, and in the table you can see that the Image J measurement of 22.2 for the 64 people in the first session was greater than that for the manual, which was only 20.34. In fact, when we test for the difference between those 2, we find that 10 of the 12 cases there was a significant difference between the 2, and where that significant difference was, the Image J measurements always came up bigger than the manual. That, again, if you think about it, isn't necessarily surprising, because when you draw a perimeter around and you ask the computer to tell you what the greatest length is, it's going to give you the right answer. So the only variability you've got is where that perimeter is. Whereas with the manual, you've got 2 modes of variability. One is where is the greatest length to start with, and the second is have I measured it correctly. Looking at outliers, this is just a plot of measurements that everybody gave for greatest length over both sessions and then ferrule's diameter over both sessions. The nice thing to note here is, firstly, that all 4 distributions aren't too dissimilar to each other, which is nice, although we have shown that there is variability. But also that we do get consistent differences. So these numbers relate to the code IDs of people of the observers. So number 33 was an individual who turned up and gave quite a large measurement for greatest length in first and second session, but also gave a large measurement of ferrule's diameter when she did it on, whoever did it on the screen. So we've got some consistency over time and across modalities. with outliers, but also less for those people who maybe see a smaller bruise. They do it across modalities and over time. So there's just a strapline saying that. So when we summarise over all 8 bruises, so it's 12 cases, what we can see is that firstly the coefficient of variation isn't too dissimilar between either GL, which is the greatest length, or FOM, which is the Ferri's diameter, but also that 11 out of 12 cases the Ferri's diameter of the electronic is smaller. There is less variation, but it is marginal. When we look at the differences between the measurements, we can again see that of the 4 images that were used in both sessions, the standard deviation was smaller for all 4 for the image J measurements. So the main findings from the study, the first port of call was feedback from people. What did they think of the study? What would they improve? There was lots of feedback on maybe standardising the actual environment in which the study took place and trying to mimic the clinician's office, for instance, when the child turns up. Also things like the colour palette. They said maybe if the colours were in strips, you can hold it against the bruise as opposed to trying to find one in the middle of that messy palette. When we looked at correlations between characteristics of the observers and the answers they gave, we found that age group and colour blindness, we did a colour blindness test on them, did affect their perception of predominant colour. With colour blindness, that's not surprising. And with age group, there has been studies in the past that have shown the same thing. And also the potential for outputting a finite colour palette in practice for clinicians to try and, for the same 3 reasons we used it in the study, reduce ambiguity and make it all better. So the 3 findings from the stats were between and within observed variation does exist. We found that electronic methods gave larger estimates than manual, and it looks like it's more consistent as well. And the outliers are consistent across sessions and methods, which it means that it's not random. So if people see a bigger bruise, they see it wherever they see it, which is a good thing when it comes to variation. So the conclusions and next steps, yes, observed variation does exist, and therefore it can be detrimental to the accurate assessment of bruises. That's going to be an issue. So what do we need to do? We need to remove the observed variation and create or find a standardized automated procedure for assessing bruise colour, shape and size. So get rid of the people sign. So therefore the next step is to find that automated procedure. We're going to go into image analysis techniques, and the first step is to find the boundary of the bruise. Once we've defined that in a standardized way, we can do all the assessment and measurements from that within image analysis. So very much that next step is a work in progress at the moment. And consequently, I know there's a few image analysis streams going on, hopefully a few of you in the audience, so I'd very much like any of your suggestions or any questions in general.
I actually don't really know what the hell I'm doing up here. I hadn't seen Gail's presentation before, and I knew that Zoe's one was fantastic. I reckon that having a slightly funny accent goes a long way at the YSM. That's about it. And also, it's kind of doubly embarrassing because I went to a few of the other talks there yesterday, and a few people are looking at the British Household Panel Survey, doing all sorts of fantastic things, latent class modelling, controlling for attrition, and all that sort of stuff. I don't do any of that, so try not to waste your time too much here. Right, so it's the life course events on mental health, and we're using the British Household Panel Survey. One day in work I was doing anything but what I was supposed to be doing. I was looking up a few papers on health economics, and it's quite fascinating. I came across this paper, and I think this was in the abstract, so I stole this from the abstract. And I think it's really interesting that somebody would think to do something like this. And there are good reasons why you might want to quantify the effect in monetary terms of life course events. So I think the example they gave in this paper was that if a judge is trying to award punitive damages to a company, or if somebody, like if you lost your partner in an industrial accident and somebody was trying to say how much is that worth, then you might want to have an actual monetary value for marriage, even as distasteful as that might seem. So what they did was that their central thesis was that money is associated with happiness, so that's wealth. And then they said, so what happens if you lose a spouse? What happens to your mental health? and then how much would we have to pay you to raise your mental health back up to the level you were at previously. And that's quite an interesting idea. We're interested in this really just in terms of the mental health parts of things. I mean, the health economics is not something that I know anything about. But I thought that was just a really interesting paper. So our research question, we're interested in sort of the social determinants of mental health, really. So we came up with 7 different life course events that we thought might be interesting to have a look at and see how they affect your mental health. So this is slightly disingenuous, actually. What actually happened was that the Welsh Assembly government put out a funding call for the analysis of secondary data sets. So we looked up the British Household Panel Survey, saw what they had, and then formulated a research question. And this is what they had, and as is always the case with these things, you get about a week to write the proposal, and then admin get about 3 weeks to get signatures. So you don't really have a huge amount of time, and I don't think I did a fantastic job on all of these. Family size in particular, I think, is one that I would definitely exclude in future, and in fact it's not going to be in the report. What we're looking at there is changes to family size. So your family size could increase if somebody, if you have a new baby in the family, that would increase your family size by 1. If an elderly or infirm parent came to live with you so you could care for them, your family size would also increase by 1. And those two are very different events, and we would have no way of separating those at the moment. Similarly, if your kid goes off to college, then your family size decreases by 1. If you lose a partner, family size decreases by 1. So I really didn't think this through. I didn't really know how I was going to interpret the coefficient that I was eventually going to get. Other ones, the social class idea. There's very little transitions in social class, really. People tend to stay in them, so we had real trouble fitting that model. Marital status was an interesting one. There's some interesting things going on there. And household income, I'll talk a little bit about that as well in a moment. Employment status is the one I'm going to focus on today. I'm not going to show you all this stuff. So, for those of you who don't know, the British Household Panel Survey, freely available to UK academics, really fantastic resource. Everything is exceptionally well documented. You can find out whatever they take the data, it's interview administered, and they calculate variables from it, and you can find out everything they've done. It's all there. Started in 1990, so they must be up to wave 19 at the moment. We're just looking at waves 1 to 15, so there's a lot of data there. And what they do is they take household as a sampling unit, so they go to households and they interview everybody in that household, and in subsequent waves, if somebody branches off and sets up their own household, everybody in that household is also included in the panel. So in that way, the survey sort of continues. And they also added extension samples, I can't remember when, but to increase the sample size for Wales and Northern Ireland and Scotland. So that's the data. And this is the major variable of interest. The mental health score as measured by the GHQ-12, so this is the General Health Questionnaire. So I don't know how familiar you are with the General Health Questionnaire, but it asks questions like, compared to usual, how much of the time have you been feeling like you're a worthless person or feeling full of energy, or it's all sort of general stuff like that. 12 different questions, multiple choice response, and you get a score between 0 and 36. And it is well validated, it seems to be measuring something. And this is the distribution that we see in the British Household Panel Survey. So it's essentially measuring number of problems that you have. A few of them get reverse coded. So high scores are bad, low scores are good. And this is the employment status transitions that we're interested in here. Bit of a mistake here. Basically, we're looking at going from employment into one of 4 different states. So that's unemployed, retired, family carer, or student sort of gets lumped together. Being on long-term sick benefits is another one. And then all of those back into employment. So we're looking at those transitions. And there's a bit of information available on this, and so people kind of know that going out of employment is bad for your mental health, and being on long-term sick benefits is also bad for your mental health. So we can tell if the analysis has worked or not. So this is the raw data. So what we're looking at here now is differences in general health questionnaire scores. So we've taken individuals and they respond for a certain number of waves. They can drop in, they can drop out. And we look at differences between consecutive waves and we see if their scores have gone up or gone down. And then we also have other indicator variables which tell us when a life course event has happened. So we might know that between wave 1 and wave 2, a certain individual got divorced, and then we can include that as an indicator variable and find out if that type of event is associated on average with increasing or decreasing mental health scores. So you can see here for going from employment into being on long-term sick benefits, the distribution is sort of skewed to the right there. So people's GHQ scores tend to go up. Higher scores indicate more mental health problems. So going from employment, where you might feel useful and you've got a purpose to your day, into long-term sick benefits, where it's very trying, then that's associated with increasing problems in mental health. And the reverse transition, coming back out into employment, it's mostly negative differences, so that indicates an improvement in mental health. So that's as we might expect. So before I go on about this, the previous talk, we were trying to figure out how we were going to analyze this, and I was convinced that we were really worried about reverse causality. So we didn't want decreasing mental health scores to lead to you losing your job. So what we wanted to do is see life course event between year 1 and year 2. We would then look at a mental health score difference between year 2 and year 3. So we could be sure that the life course event has happened before the difference in mental health. And I fitted that, and I was getting all sorts of crazy answers, and that's actually what I presented at the YSM. So I was getting protective effects of divorce and protective effects of losing your physical health, and it was all a little bit odd. So I went back and we were looking at it, and obviously this didn't fit with any of the rest of the literature. So we looking at if a life course events happen between year 1 and year 2, looking at the mental health score change between year 1 and year 2. So we are leaving ourselves open to the possibility of reverse causality here, but there is enough literature to indicate which direction these things go as well. So well, that is certainly a flaw. Our response variable is changes in general health questionnaire scores, and we include lots of different life course events. So there was a few modeling issues here, 190,000 responses. Trying to fit hierarchical models to this was a bit tricky. We eventually managed to get a few of them. But basically, at the moment, what we've done is looked at them all separately. So each of these different life course events are not fitted simultaneously. We just look at the employment transitions first in a single model. And so this is one of the nicer ones that sort of makes a little bit of sense. And so I can just explain here. This is going from employment into long-term sick benefits. And in the first year, you can see there's an increase in GHQ score of about 3.5. So that's after the event happens. So there's a sharp drop in mental health score. But then people are resilient. So a year again after that, people are slowly on the upslope, so that they've had their sharp drop and they're slowly getting better. But the mental health doesn't actually ever get back up to the level that it once was prior to unemployment. And as you can see here, what I was doing previously was looking at starting at number 2, and I was getting the wrong answer. I was getting a positive difference or a negative difference, which didn't make any kind of sense at all. So we're much happier with this now, and the other transitions are also making a little bit more sense. This is the household income variable. So this is fitted as a linear effect, and we're looking at doing this in lots of different ways. I think really we don't really want to fit it as a linear effect. What this indicates is it is significant, but you would have to increase your income by 1/3 in order to increase your mental health score or decrease your mental health score by a single point on a 36-item scale. So we're kind of saying that money doesn't make you happy. Okay, so to summarize, I think I whistled through that there. The literature is pretty strong on indicating that being on long-term sick benefits is very bad for your health, and that employment is very good for your health. So it's reassuring that that's also the largest effect that we saw in all of our employment status transitions. So there's other ones as well that are significant, but I haven't gone into them today. The thing that I think is most interesting is that the resilience sort of factor that people do bounce back after these things, and that mental health, the differences in mental health seem to occur very quickly after transition. I have to, that's pretty much it for the moment. I have to acknowledge the Welsh Assembly government for funding this stuff, and when I presented this back in Easter, I was complaining about them imposing very tight deadlines on us and that we would have a far better analysis if they gave us a bit more time. It's now September and we still haven't actually submitted the report, so I should really be complaining about myself for not actually doing it. That's it. Thank you very much.